LeChatlier's principle lets us figure out what is going to happen when a stress is put on a system at equilibrium. We can figure out what's going to happen by looking either at LeChatlier's principle or collision theory. LeChatlier's principle says when a change is imposed on a system, when we stress a system that's at equilibrium, the equilibrium will shift to undo whatever it is that we have done to the system. What you need to remember is that at equilibrium, the rates of the forward and reverse reactions are equal, which makes the concentrations of the reactants and the products constant. When we apply a stress to a system that's at equilibrium, the rates of either the forward or the reverse reaction, or both, are going to change. This is going to allow a new equilibrium to be established, but it is going to have different concentrations than before that stress was applied. So if we look at this reaction here, A plus B at equilibrium with C plus D, we have the reaction proceeding in both the forward and the reverse directions. We don't know how much of anything that we have at this point, and we don't need to know that. All we know is we have constant amounts of A, B, C, and D because the system is at equilibrium. Now we're going to apply a stress to it. The stress that we're going to apply is that we are adding reactant A. So there's now more A has been dumped into our container. So if we think through this in terms of collision theory, we added in more particles of A. Those particles are going to be colliding more often. So the number of collisions between A and B is going to increase, which means the rate of the forward reaction is going to increase. We started off with equal rates for the forward and reverse reaction. Now the forward reaction is speeding up. I didn't do anything to change C and D, so that reverse reaction is going to proceed at the same rate. My system is no longer at equilibrium because the rate of the forward reaction is now faster than the rate of the reverse reaction. This means that I am going to be producing the products faster than I'm using them up. So my amounts of products are going to increase. Likewise, I am producing more reactants slower than I'm using them up, which means the amount of my reactants is going to decrease. This is defined as an overall shift to the product side, or a shift to the right. Whichever reaction is going faster, in this case the forward reaction, is the direction of the shift. Everything in the direction of the shift, those concentrations are going to increase. Everything on the side away from the direction of the shift is going to decrease. Notice we're not really saying what is happening to A overall, because I added some and then it's getting used up. So what's going on with A is a little complicated, but we can say for certain that there will be less B in my system at equilibrium than there was before I added that extra A. So let's go back to equilibrium. And this time we are going to remove some of the product. We're going to remove some of C. Well, in this case, we are removing some of the product, which means the collisions are not going to happen as often. So that reverse reaction is going to slow down. My forward reaction doesn't change. So again, I'm not at equilibrium anymore. My forward reaction is proceeding faster than my reverse reaction. So I'm producing the products faster than I'm using them up. So my reactants are going to increase. My products are increasing. Once again, my reactants are being used up faster than I'm producing them, so my reactants are going to increase, which again is a shift to the right. So notice either adding a reactant or removing a product is going to shift the reaction to the product side. The amount of the products is going to increase. The amount of the reactants is going to decrease. Now we just did this in terms of collision theory, but the same thing works with LeChatlier's principle. Whatever I do, the system tries to undo. I add A. Well, the opposite of adding is going to be using it up, trying to get it back down toward where it started. So by adding A, the system's going to try to use up A. But in using up A, it's also using up some of B. And that A and B are turning into products. So C and D are increasing. When I remove a product, the system's going to try to replace what I took out. Well, as it replaces C, it also has to create more D. So D is also increasing. And in order to get more of those products, we need to use up some of those reactants as well. Now, we can also add heat or change the temperature of a reaction. In order to look at that, we do need to know which side of the reaction heat is on. In this case, heat is a reactant. When I increase temperature, that's just like adding heat. Now we know that increasing the temperature is going to speed up the rate of a reaction, both the forward and the reverse reaction. But it's going to speed up one of them a little bit faster. So we can't really do this one in terms of collision theory. But in terms of LeChatlier's principle, whatever I do, the system tries to undo. In this case, I add heat. I increase the temperature. The system's going to try to use it up. Well, the one that's using up heat is the forward reaction. So that means the forward reaction is going to be favored. And I am going to end up with more products. And in using up heat, I'm also using up A and B. So by adding heat, which is on the reactant side of the equation, essentially I'm adding a reactant, it shifts away, it's shifting toward the product side, using up the heat and the other reactants that are there. So regardless of whether it's heat or a chemical, if I add a reactant, it's going to shift to the opposite side. If I remove a product, it shifts toward the product side. Now I could also remove reactants or add products, but in general, we tend to think of the product as the thing that we're wanting, so we're trying to do something to shift it toward the product side. But in the same way, if I added a product, it would shift it toward the reactant side, trying to use up that product. If I were to remove a reactant, it would shift to the reactant side, trying to replace the reactant. The other thing that we need to look at is pressure. And it's important to remember that pressure will only affect gases. And if I have equal moles of gas particles at the same temperature in the same volume container, they will have the same pressure. So when we're looking at an equation, we want to look at how many gases are on each side. In this case, I have 2 moles of A, which is a gas, and 1 mole of B, which is a gas. So I have 3 moles of gas on the product side, or reactant side, and 2 moles of a gas, 1 mole of C and 1 mole of D, on the product side. If I were to increase the pressure, the system is going to try to get the pressure back down to where it was. Well, fewer moles of a gas are going to have a lower pressure. So if I increase the pressure, it's going to shift to the side that has fewer moles of gas, which means the side that has fewer moles of gas, that stuff is going to increase. In this case, I would produce more moles of C and D. using up my A and B. The side with more moles of gas is going to decrease. The side with fewer moles of gas is going to increase. If I were to decrease the pressure, the system's going to try to get the pressure back up to where it was. Therefore, it's going to shift to the side with more moles of a gas. The stuff with more moles of a gas is going to increase, and the side with fewer moles of a gas is going to decrease. Again, remember, we're only dealing with gases. If this reaction, instead of this, had said B is a solid, so that I have 2 moles of A, which is a gas, B being a solid, we would ignore, C and D, 2 moles of gas on the product side. So in this case, where I have 2 moles of a gas on the reactant side and 2 moles of a gas on the product side, changing the pressure will not shift the equilibrium because the moles of gas are the same on both sides. But if I have unequal moles of gas on either side of the reaction, then changing the pressure will shift the equilibrium. Adding a catalyst will never shift the equilibrium because catalysts will speed up both the forward and reverse reactions equally. So it will allow something to establish an equilibrium faster, but once I have that equilibrium, it's not going to change the amounts that I have present. So just to summarize, if I add something, it shifts away to the other side. So looking at your reaction, if you're adding something that's a reactant, it will shift it toward the product side. If I add something that's a product, it will shift it toward the reactant side. If I remove something, it's going to shift toward the side that has the thing I took out. So if I remove a reactant, it will shift toward the reactant side. If I remove a product, it will shift toward the product side. And if I increase the pressure, it will shift toward the side that has fewer moles of gas particles in it. Again, that shift direction tells you which side is increasing. If I'm shifting toward the reactant side, that means I'm producing more reactants. The concentration of reactants will go up and the concentration of the products will go down. If I'm shifting toward the product side, then the concentration of the products will go up